Illustrative Math, Geometry. Unit 1, Lesson 15 is called Symmetry. We're only going to be talking about reflection symmetry, not rotational symmetry. That'll be the next lesson in Lesson 16. All right, so our goals today are I can define reflection symmetry, I can determine if a figure has reflection symmetry, and I can find lines of symmetry when given a figure and draw figures that have a specific number of lines of symmetry. So here's our warm-up. Here is segment AB. If you translate the segment up 5 units, then down 5 units, it looks the same as it did originally. What other rigid transformations can create an image that fits exactly over the original segment? Okay, so anything with a translation that moves it left and then right the same number of units, or right and then left the same number, or up and down, or down and up the same number of units. So, most people in class, they would say something along the lines of, keep it similar. They'd say translate right 6, then translate left 6. Okay, but you could also do a couple other things too, as far as reflections and rotations. So on to number 2, are there any single rigid motions that do the same thing? So if I knew where, if I constructed the perpendicular bisector here of this segment, so or if at least I knew where the midpoint was of this segment, but I'm going to go ahead and go back and do a construction. So you center a circle at A, I center a circle at B, radius AB, and then that line right there where those two intersection points meet is the perpendicular bisector of AB. Okay, so if I reflect this segment across the perpendicular bisector, it'll be the same image because B will go to A will go to B, and then they'll be congruent. So, you would get your B prime would be over here, your A prime would be over here, and this segment right here would still be the same. Okay, so, I would write something along the lines of reflect segment AB across the perpendicular bisector of segment AB. There's also rotational symmetry. If you knew the midpoint, like right here, if I rotated 180 degrees centered at the midpoint, that would work as well. But we'll get more into that tomorrow, but I'll show you here. Right there, centered at M, 180 degrees. It's the same thing. Now, my picture was a little off, but kind of get that right there from the rotation. Okay. So if it rotates to the same image, we say that it maps it onto itself. Okay. We'll talk a little bit more about that as we move on here. So what is a line of symmetry? A line of symmetry for a figure is a line such that the reflection across the line takes the figure onto itself. Okay, so basically that means for this hexagon here, if I reflect across this line, I am going to get the same shape. Okay, so I'm going to get this hexagon right here after I reflect it. Okay, so this point, if this is like A, my A prime comes over here. And if this was B originally, my B prime goes over here, and so forth. Every point is going to flip-flop back and forth, and you get the same exact shape. So here's a couple examples here of reflection symmetry. If you forgot what a reflection is defined using a line, takes a point to another point that's the same distance from the given line and is on the other side of the given line. So the segment from the original point to the image is perpendicular. So basically, M here is the perpendicular bisector of the segment that's being, or of the segment created when you connect the image and the pre-image. Okay. Reflection symmetry. figure has reflection symmetry if there is a reflection that takes the figure to itself, okay? Kind of just like I showed you up here with the line of symmetry, okay? Same thing here, this one has more than one line of symmetry. If I reflect across this horizontal line, this gets flipped to down here. So I'll use two different colors so you can kind of see. The red goes to the blue goes to the red. If I reflect across the vertical line, here's the blue goes to the red. And this part here that's on the line, that stays the same. Any point on the line of symmetry or the line of reflection will not move, okay? All right, so what we're gonna do is we're gonna draw lines of symmetry. So a rectangle that is not a square. So I put definitions down here below because it is kind of crazy how many high school kids don't know what a rectangle is. So a rectangle, you need 4 right angles. That's all you need to be a rectangle, 4 sides and 4 right angles, okay? So the only lines of symmetry on here will be right down the middle and right there, okay? Now, I might be a little off on this here, but right about there. Now, a lot of things that kids do is they think that a diagonal on a rectangle is, but it's not, okay? This is wrong. I'm going to show you here, this is not a line of symmetry. It does cut the area in half, but that does not mean it's line of symmetry. So I put it here in red. Just because the area is cut in half does not mean it's a line of symmetry. Because remember, if I were to draw, like let's take this point here. If I were to reflect across this diagonal here, remember, it's going to be perpendicular. So I'm just going to estimate a perpendicular line, and it's going to be equidistant from there. So if I use my compass here to kind of measure the distance, and again, my perpendicular is just an estimate. It's not accurate by any means, but it looks pretty close to a right angle. But you can see that that point would go way down here, okay? So, if this was B, B prime would be down here if I'm reflecting across this line. So you can clearly see that we're not going to get the same rectangle. It's not going to map itself onto itself. So don't accidentally do that. Don't accidentally think that diagonal is a line of symmetry just because it cuts the area in half, okay? A regular pentagon. So this will actually have 5. You just go right through every vertex to the other side so that it intersects it at a perpendicular. And again, I'm just roughly drawing them in here. They should all kind of go through this same point right here in the middle. But you can see that if I were to fold it on that line, it would be the exact same thing. A good technique if you're doing this on paper, or sometimes I guess you can do it on your computer too if you lay your screen down flat. Trace the figure and use tracing paper. And if it folds in half right on top of itself on your line of symmetry, then you have reflection symmetry. So a good thing, what I always do in my class with the kids is to see that rectangle, that diagonal is not a line of symmetry. I have students trace the rectangle on tracing paper, and then I have them fold on the diagonal, and they can see right away that it does not line up, okay? Whereas if they fold it on this line, this side goes over here, and this side goes right there. It folds just like a book, okay? A regular pentagon, I also put the definition here. Remember, regular means that you have congruent sides and congruent angles. Equilateral triangle, that will have 3 lines of symmetry right through there. All right, basically the height of the triangle, okay? An equilateral triangle has 3 congruent sides. An isosceles trapezoid. So you have one pair of parallel sides. So if you look up here, this top and bottom are parallel, and one pair of congruent sides that are not parallel. So these sides here are congruent, okay? So it's kind of like an isosceles triangle, but you chop part of it off and kept the bases parallel, okay? So this one will only have one line of symmetry, and it's only right through the middle. Because again, if I fold this over, they'll map right on top of each other. The diagonal will not be, okay, so I'll draw it here. And again, kind of just like with the rectangle, remember, if I reflect this point, so let's try to swing this so that it's perpendicular as best I can, something like that. So this distance here is going to be the same. So you can see that this point does not go over to there. It's going to go down here. It's not going to work. Okay. So no, do not draw the diagonals. I know it cuts the area in half, but it's not a line of reflection. All right. A rectangle that is a square. Square is 4 congruent sides and 4 right angles. So the squares actually will have 4 lines of symmetry. So right down the middle, right down the middle. And important to note, this point here has to be the midpoint of that side, and this has to be the midpoint of that side. These would have to be midpoints of these sides as well. The diagonals will work on a square because look at your diagonals here. They're perpendicular. And if you measure this distance with the compass and this distance with the compass, they're going to be the same. Okay, so if I wanted to reflect this point right here, let's just call this point A. A prime would go over here because, again, it's when you reflect perpendicular and bisector. So this line is the perpendicular bisector of A prime. Okay, and if you want to check it with a compass, you could just measure them. And again, mine's not going to be perfect because I just kind of whipped it up there real quick. I didn't like measure that angle perfectly, but you can see that those are pretty much the same distance. Okay. A parallelogram that is not a rhombus. So a parallelogram, you need 2 sets of parallel sides. A rhombus has 4 congruent sides. A rhombus is also a parallelogram, but it has 4 congruent sides. So again, if you want to trace this, if you got tracing paper, trace this parallelogram. Pause the video, start folding your tracing paper. But this actually is going to have none. Okay, this is going to have no lines of symmetry. And again, think about it. If you well, maybe it will actually. Actually, it will have one. It will have 2. Actually, I lied. It won't have any diagonal ones, but it will have 2 right there. Oh wait, no, maybe not. No, it's not. I was right. So if you look at this, okay, let's look at this one. Okay, so from here to here, okay, you can see that this line is not perpendicular. Okay, so this point right here, if I was gonna reflect it, it's not the perpendicular bisector of this segment. Okay, it's not perpendicular to reflect that point. So if I were to reflect across this line, I would have to draw a perpendicular. Whoops. I would have to, perpendicular to this line. So this point is going to end up somewhere down here. Okay, so that's not going to work. So this actually has none. Okay. A parallelogram that is a rhombus. Now this one's going to have 2. It's going to be the diagonals. Okay, and if you look there, you can see that they look perpendicular. So this is going to be equidistant. So this point, if this right here is, if this is A prime would go over here because they're the same distance and they're perpendicular. Okay, we haven't proven that they're perpendicular, but we're just kind of going off of eyeballing it and using what we know to see. And if this was B, this would become B prime. Okay, if, this right here, same thing here. If this is my line of reflection, this is C. C prime will, go over here and so forth. Okay, so it looks like we have 2 there. Now, a circle has infinitely many because really any diameter, as long as you have the center here, if you have any diameter, I don't know why that became solid. I wanted it to be dotted, but go back here. There you go. Any diameter, I'm going to reflect across there. Every point is going to be, look at this point right here. This point, same distance as here and perpendicular. Okay, and you could, basically reflect any point across that line. It would always work. So you could draw as many of these as you want. Any diameter has to go through the center. So infinitely many lines of reflection. Okay, it's got to be a diameter. Again, remember the circle definition: set of all points equidistant from a fixed point called the center. Rhombus, I mentioned it earlier, 4 congruent sides. It's also, every rhombus is always a parallelogram as well. Okay, and you can see here, this side here looks parallel to that, and this side looks like it's parallel to that side. So you can kind of tell that it's a parallelogram, but it's more specific because these sides are all congruent in length. All right, so here's a couple more examples. If you want to pause the video and take a look at them, take a screenshot. Here's one line of symmetry. I flip over across there. Here's 2. Here's 3. Here's 4. This one has none. Okay, if you ever want to draw one that has no lines of symmetry, that would be a scalene triangle. Okay, those are always good ones if you ever are looking for a figure with no lines of symmetry. Here's one with 4. Oh, I did the same one twice. I don't know why I did that. Okay, here's one with 5. Here's one with 6. This kind of looks like a pentagon, looks like a regular pentagon. You can kind of tell here if I were to, it's kind of the same thing as a regular pentagon. You just, fits right in there just like that. So it's just kind of changing the shape to mess with you here. This is kind of like a regular hexagon too. If you look here, you can kind of see it. Whoops. So looks just like a hexagon. They just kind of modified the shape a little bit to make it look different. But there you go. All right, there's your lines of symmetry. All right, a kite. A kite has 2 pairs of consecutive congruent sides. So this side here is congruent to that, consecutive meaning next to each other. And this side is congruent to that side. So it's kind of easy because everybody knows what a kite looks like. So there it is. All right, Kieran thinks both diagonals of a kite are lines of symmetry. Tyler thinks only one diagonal is a line of symmetry. Who's correct? So draw your diagonals. And I think this one's good right here, because if I reflect across this line, it will be a mirror image. This one will not, because you can, again, clearly tell when you look at it, you can check it with a compass or, a ruler or tracing paper. You can see that this is not, like this point right here, if it was going to reflect across this line, it would go right there. If this was A, this would be my A prime, which is not in the right spot. So that's no good. Okay, so only one. So Tyler is right. Okay, so kites do not have two. All right, sketch shapes which have the following symmetries, and write a transformation statement for each one. Look at a sentence frame in the definition of reflection in your reference chart if you get stuck. So one line of symmetry. Good one for that would be an isosceles triangle. So one line would be something like that. So here's my line of symmetry right there. So let's name the line. Let's call this line R for reflection. Let's call this triangle ABC. So write a statement here. I would say reflect triangle ABC across line R. Okay. And when you see that, it maps it onto itself, and there it is. Okay. Two lines of symmetry. Let's go back and look at some of these that we had. Anything with an X. So any type of rectangular shape maybe would work. Rectangles only have two lines of symmetry. So for my two, make sure it's a rectangle that's not a square. So here we go. Here's one. Here's two. So let's name this M N O P. Let's call this line L and line M. So for this one, I would say reflect MNOP across line L, or line M. 5 lines of symmetry would be some sort of regular pentagon type of shape. Probably be the easiest. So there's that one. So A, B, C, D, E. Draw your lines of symmetry. So you're going to go vertex down to the other side. Make sure you're perpendicular. They should all go through the same point. And there they are. So let's call this P, line Q, line Y, line Z, line S. So there we go. And I'm going to write my transformation. I'll say reflect regular pentagon A, B, C, D, E across line P or Q or Y or Z or S. Okay, any one of those lines will work. Let me move this down so you can read that. All right, I guess I could have said reflect rectangle, or not really necessary as long as I name the points. Same thing there with the regular pentagon. So, all right. Last thing here, what happens to the diagonal of a rectangle when the rectangle is reflected across a line of symmetry? So the diagonal will become the other diagonal. Okay. So if I were to, remember, rectangles only have two lines of symmetry. Okay, right there and right there. So look at your diagonal here. This diagonal. Okay, if I reflect across, let's do the vertical one. Okay, so let's get rid of this one here just for the heck of it. If I reflect a point, I'm just going to pick a couple points here. Remember, when you reflect across, it's going to be perpendicular and equidistant. So this point will be equidistant over here. So, if I measure this, right there, go right there roughly. Same thing here, this distance, I got to draw perpendicular. This distance will be equidistant right here. So what you start to see is these all line up and you get, and pardon my picture, this point is a little off, but it should have been more like right there. So a little off, but anyways, you get the same exact, you get the other diagonal. I think it was off because my line of symmetry is off here. You can tell that it doesn't go right in the middle, but again, I just estimated it. But so your answer is you get the other diagonal. So this suggests that the diagonals of a rectangle are always congruent. Okay. This is actually a very, very useful concept. I actually use this all the time. Like when I'm doing projects at my house, if, I'm doing any type of, laying concrete or, any type of carpentry things, and I need something to be a rectangle. If I'm cutting it out of a board or something, I'm measuring things, I always use protractor type of thing to make my angles, but then I double check the diagonals to make sure they're always congruent so that I know it's a perfect rectangle. So kind of cool. But yeah, anyways, thanks for watching this video. Hopefully you enjoyed it. If you need any help on this, we're gonna be doing a little bit more here with reflections and rotations as we move forward in this chapter. So we'll see you next time. Thanks for watching.